Next up, we have Dr. Mark Clampin, who is our Division Director for NASA Astrophysics. Come on up, Mark.
Okay, good afternoon, everybody. So this is a little unusual, having an astrophysics talk at the AGU, but there's a significant degree of overlap in many of the areas that we work on. So we thought it'd be a good idea to talk to people about what we do in astrophysics. I'm Mark Clampin. I'm the Director of Astrophysics at NASA. And I'm going to start off by just showing a by the numbers chart, just to give you some idea of the scope of what we do. So we have about 14 operating missions right now, with another 15 missions in development right now. And we do many of the same things that the other three divisions that you hear about at AGU so often are involved with. We develop technology for future missions. We do a lot of research and analysis that supports the data and the science that we do with the missions that we build and fly. And we also have a very active program of small sats, sounding rockets and balloons that we work with the heliophysics division to make sure that we're developing new technologies and providing additional opportunities to do astrophysics science. So I'm going to talk to you today mainly about some of the science highlights of the things that we do and really nice results that we've had this year. And I'm going to start off by talking about eclipses again. So this isn't our big U, but we do a lot of work with transit science, which are mini eclipses when exoplanets pass across the face of their star, the parent star, and allow us to get idea about the size and composition of those exoplanets, and also to disperse the light and measure the atmosphere of the exoplanets. And both the Kepler mission and now the TESS mission were very active in finding small rocky planets. TESS in particular has been really finding small rocky planets around nearby stars. And with the James Webb Space Telescope, we're now in a position to do a lot of follow-up work and actually study the atmospheres of other exoplanets around stars. And then that, of course, allows us to do comparative planetology, comparing them to the planets in our own solar system. So over here on the right, you see really interesting recent observation. This is K2-18b, and this is one of the first detections where we have methane, carbon dioxide, and also some very interesting tentative detections of dimethyl sulfide, which of course require a lot more observation to really confirm them. But it's very interesting that as we start to get more and more of these kind of observations with the James Webb Space Telescope, we're opening up a whole new field of astrobiology and planetary science, working very closely with our colleagues in planetary science to be able to model these atmospheres and really start to understand, you know, what's going on with these exoplanets, whether they're potentially habitable, and also if they even have atmospheres. So another one that Webb has looked at this year is one of the TRAPPIST-1 system, which is 7 small, relatively Earth-sized exoplanets that orbit the TRAPPIST-1 star. And JWST has already determined that the closest star in that system is actually almost certainly devoid of an atmosphere, much the same as Mercury is. So we're really starting to make a lot of progress in understanding exoplanets around other stars. And you know, some of the other recent results that have come from these observations, an example here where we have the first example of photochemistry detecting sulfur dioxide in this particular exoplanet. So you can see the quality of the spectra that we're getting here, and this is around planets around other stars that are, you know, within a couple of hundred light years. So we're really starting to break down a lot of the barriers that we had before the James Webb Space Telescope that really prevented us from studying exoplanetary systems outside our own. We also do a lot of work in the field of high energy astrophysics, in particular studying X-ray and gamma ray emissions. And I've got a few really nice examples here. So this is an example of a black hole in a very active galaxy. You can see a jet here. And on the right-hand side, we have an image that was taken with a mission we call IXB, which is an X-ray polarimetry mission. So IXB, for the first time, is allowing us to actually understand the nature of what's going on in these jets and really start to decompose the physics and identify what's driving these jets and the nature of the particles inside these jets. On the right-hand side, you see a really interesting result came out a few weeks ago. So James Webb, as it does its very deep observations of the early universe, and James Webb was designed to find the very first galaxies that formed in the universe. James Webb has been finding a lot more galaxies in the early universe than we expected, and many of them are extremely massive, and we determine the mass from the light. So James Webb is already, both addressing the primary goal we built it to do, but it's also finding new problems with our understanding of what happens in the early universe. So there are a number of theories right now about how we got so many of these massive luminous galaxies, several 100 million years after the Big Bang. One of them is that maybe they're being seeded by black holes. And this is a detection here of a black hole that's 600 million years after the Big Bang. And not only was James Webb able to see it with its very deep field image, but for the first time we were able to detect the black hole's X-ray emission using the Chandra Space Telescope, which is an X-ray telescope. And the reason is because the white galaxies you see in this image are producing what's called a gravitational lens. They are bending and magnifying light from galaxies behind them, and we actually are able to see that the gravitational lens has magnified the X-ray flux from this black hole so much that we can actually detect it. So we're starting to use these gravitational lenses as laboratories to understand what's going on in the early universe. We also use Hubble and Webb to study the nature of star formation, and this was a really nice result this year, showing this stream of star formation here, where a black hole has passed along this path, produced shocks in the gas and dust on the outer regions of a galaxy, and created this sort of trail of star formation. And then over there on the right, we also have another example of a very active black hole at the center of a galaxy. And again, we're able to do a really good job of trying to pull apart what's going on in these extremely active systems. And of course, one of the big fields that people come to talk about here at the AGU is planetary science, and James Webb is making a really major contribution in this area. For me, one of the most exciting results this year was the discovery of this outflow from Enceladus. So rather than the sort of very relatively constrained geysers that you see in the earlier images, James Webb has shown that there's 20 times more water coming off of Enceladus, creating this big plume, which is then feeding into a torus that orbits Saturn. So this was a really nice and unexpected result. Nikki Fox already talked in some detail about Jupiter and the observations of the aurora and the very high energy red spot and hazes in the atmosphere. And we were also this year able to detect a very rapid jet stream in the upper atmosphere of Jupiter. Over here, this is a really nice result that was just published. And the idea here is that we've known for a long time that there are a couple of different ideas about how we get water into the inner regions of the solar system where small rocky planets form. And Webb has been able to show that when you have very compact disks, there's very effective transport of water into the region of these disks where rocky planets form. So we've really been able to sort of validate some of the models about the transport of water and volatiles within forming protoplanetary systems. And then finally, over here on the bottom right, this is a near-infrared spectrum of a Centaur asteroid, showing that there's a significant amount of water ice frozen on the surface of this asteroid. So Webb is also making a really major contribution to planetary science. And I wanted to finish up a bit by just spending time talking about the future. So the James Webb Space Telescope has been operational now for about 2 years. We just had our third round, and the number of proposals has gone up from 1,600 to 1,900. So it's now about 10 times oversubscribed. On the right, or my right here, is the Roman Space Telescope. And Roman is our next big flagship mission that's designed to study the nature of dark energy, which is this mysterious force that is making the universe accelerate as it expands, and also dark matter, which is an unknown property of galaxies, that there seems to be a lot more hidden mass than we can see in the optical and the near infrared. So Roman is our very first flagship that will do surveys. Nearly all of NASA's astrophysics flagships to now have been point and shoot. So Hubble, Chandra, Webb are all programs where we go to specific targets, take images. Roman instead will actually survey a large portion of the sky. And in fact, it's going to conduct about 4 different surveys. Some of them trying to address the nature of dark energy. Some of them are also studying the galactic bulge, looking for gravitationally lensed planetary systems. So using Roman, we'll also be able to get a much better handle on the eta sub-Earth, the probability that every star has a small rocky planet. And that's very important because the next large flagship that we're just starting to work on right now is the Habitable Worlds Observatory. And Habitable Worlds Observatory was recommended in the 2020 Decadal Survey. It's a 6-meter plus large space telescope that will be designed to image all nearby stars to look for habitable planets and then characterize them for biosignatures. So one thing to remember, James Webb studies a lot of exoplanets, but they're all transiting exoplanets. So it's studying about 5% of the population of nearby exoplanets, because most exoplanets do not transit or eclipse their parent star. So Habitable Worlds will conduct a systematic survey of all nearby stars to image these habitable planets and then take spectra to get the biosignatures. What does that mean in practice? Well, it means that this telescope will have to have something like a factor of 100 times improvement in stability compared to Webb. So Webb was a nanometer class project. This one will take us into picometer stabilities, and it requires something like a factor of 100 to 1,000 improvement in contrast for coronagraphs, which are the instruments that we'll use to suppress light from the central stars so we can image the region where we're looking for habitable planets. So with that, I will finish and hand over to the next speaker, Mark Subarow.